Okay, so how the internet works. So, the internet's this funny thing that in my lifetime, it has really made revolutionary changes about a lot of different things with communication, right? So, lets us do things that really were impossible not very long ago. Number one, instantaneous worldwide communication. When I was your age, before, internet was a household thing, if you wanted to send a message to someone on the other side of the world, right? You wrote a letter, maybe you put it in airmail, got there in a few days, maybe you put it in regular mail, went a couple weeks on a boat to get there. Or you placed a very, 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 very expensive phone call to make it happen. Now, you send an email, do a video chat, anybody, anywhere, anytime. Number two, streaming music and movies, right? When I first met my wife, when we moved in together around 2008, uh, we had a Netflix account where you'd get the DVDs in the mail and you'd watch them and you'd put them in the little sleeve and send them back in the mail, right? Around somewhere after 2010, they started doing the streaming thing and we got on board with that. And you guys, probably most of you remember a time before streaming was pretty common, right? Maybe you were pretty young then, but I'm sure you remember it. Likewise, social media and groupware. Facebook for whatever, for good or bad, it's out there and lets people connect a lot. Other things like, Twitter, and of course, groupware. So groupware, all the stuff that we use like Zoom to record meetings again from, get people together from all over the world. When I was your age, if there was bad weather, what would happen is there was a snow day, you'd just stay home. Snow days are done, right? No more snow days. Now everybody just say, oh, we're going to do this remotely. Although it may happen one day that they have, no internet days if the whole internet goes out. Anyway, the thing about internet, every generation has their thing that it's new and incredible to them. And then the next generation grows up with it as just the background noise of life, right? So for you guys, internet is just something that's there, like sidewalks, probably don't think too much about it. For me, I remember a time before the internet and it changed a lot of stuff. Every generation's got stuff like this. For my parents, it was probably TV, and TV didn't become a household thing till the 50s. They grew up in houses without TV. TV came later. For my grandparents, who are actually, my parents were old when they had me, and my grandparents were old when they had my parents. I had one grandfather in World War I, and my other one was too old for it. They grew up well before radio. They grew up in a world where having electricity in your house was kind of shocking, so that was their situation. And then, their kids are like, oh yeah, electricity. Everybody has electricity. Why wouldn't you? So for you guys, internet is the background noise of your life. I don't know what's gonna be the thing that the next generation can't imagine living, without. Probably AI, could be other stuff. Okay. So we've all got our things. So that's my perspective on the internet. And I would say, if you ask me what is humanity's single greatest engineering achievement, I would say the internet, in terms of complexity, in terms of scale, in terms of all the components that have to be invented for this thing to work the way it does. It's pretty incredible and continuously updated, right? It's one thing to build one rocket that you fire once and boom, done. The internet is this massive worldwide system that is continuously in operation, continuously updated, and all sorts of, backup protocols around how it works. Things like how web pages are designed, how messages are delivered, how security is applied, all that stuff. So internet is always on, never shuts down, right? It's always there somewhere. Now your router may catch fire, but the internet as a whole, it's always there. Number two, never noticeably congested, right? Individual sites on the internet, sure, those might get busy. There were a few things I remember back in the late 90s. What broke the internet was a Victoria's Secret event that was streamed live, and a lot of people tuned into that, and the internet basically shut down. But that's pretty unusual. And at this point, doesn't really happen, right? The internet's not going to shut down, but individual sites might. Mostly free. Once you pay your ISP, your internet service provider, once you pay them, pretty much anything you want to do online is free, right? There might be stuff behind paywalls. Content access is a different issue. But even for demanding applications that require a lot of data to be sent, like voice over internet, video streaming, whatever, all that is free. You go to YouTube, watch videos all day. And finally, mostly uncensored, for better or worse. In a lot of ways, censorship is a bad thing, but pretty much it also has its place, right? Sometimes people are happy with certain content being censored, other times people aren't, but it's what's out there. There's a lot of information. Now, circling back to the whole thing about, growing up with internet versus growing up without it. For people my age who grew up without the internet, they knew how to learn things. Uh, and the internet was this neat, magical thing, right? So you already had some core of knowledge about a topic. And if you wanted to learn more, the internet made that very easy, right? You already knew some stuff. You went out and you looked up all sorts of more detail on it, right? For people that are perhaps a little younger, right? You may have grown up with the internet. Just like I talked about, it's dangerous that AI can turn into a crutch for people, that people have AI do things for them that they haven't learned how to do for themselves. I feel like there's been some of that with the internet too, that it's made data so very easy to look up that, a lot of people may, a lot of people, what can you say? A lot of people aren't learning the stuff in the first place. They say, well, anything I want to learn, I can just go look it up. And, there's definitely a lot of information out there that, way more than you can keep in your head, right? But it is really important to have a base skeleton of knowledge about any topic you're interested in. So, for example, suppose you go to France and you want to have a conversation in French with some people over there, right? You got to learn basic phrases like bonjour and ça va and things like that, right? Uh, if you're looking up every single word in a phrase book as you're having the conversation is not going to go well. I mean, yeah, you can drag yourself through it, but it's just not going to be pleasant. And this is the sort of thing that I try to do with this course. All right. So we've reached a point where now I can kind of talk about this and you can see what I mean, maybe, is that I'm trying to give people a basic skeleton of knowledge about IT. All right. Now, if you're not an IDS major, maybe you're not that interested, but if you're an IDS major, one day you're going to have job interviews, right? And the job interviews are going to ask you about skeleton type knowledge, right? They're not going to be able to ask you about particular implementations of technology at that business because you're just not going to know, right? What they're going to do is probe a little bit to see if you know some stuff. So you might sit down for an interview, right? And, the guy says, oh, I see you went to UIC. I went to UIC. And you're like, oh, cool. And he looks through the list of courses you took and say, oh, IDS 200. Hey, is that guy Lundquist still there? I took that with him. And you're like, yeah, Lundquist still there. I took it with him. And he'll be like, oh man, his exams still rough. They were something. And he's like, no, he doesn't do exams anymore. Oh, wow, you don't have exams. Oh, you got it so easy. Okay. Well, tell me what you know. Do you guys still talk about Google ads in that? And he's like, yeah, of course we talk about Google ads, right? Because Google still does ads, big thing. He's like, okay, tell me about the difference between AdWords and AdSense. And if your response is, Google shows ads and they make money, right? You're not going to impress the interviewer. But if you can say something like, oh yeah, AdWords, that's ads shown along with search results. And those tend to work really well because, if you have one set of search terms, those results are probably going to be comparable to another batch of very similar search terms, right? So you understand and Google can figure out it works well. AdSense is going to be ads that are shown on like other people's sites, like blogs. And yeah, they work well enough for Google to make some money, but it doesn't work nearly as well because, you can't count on having search terms there. So you kind of have to figure out what the site is about. And that kind of matching is a lot less exact. And if you have a good, sensible answer like that, the interviewer is going to be like, damn, look at you, you know some stuff, right? So it's just a good look. Now, again, not all of you are going to be IDS majors, so fine, but anything you're doing as far as stuff you want to be interested in, right, for whatever your major is or other stuff, start with having that kind of skeleton of knowledge so that you can, have basic understanding of these core concepts and build on them if and when you need to. Okay, so that's my soapbox. Anyway, let's do some questions. All right, so first question is number 30. Okay, which of the following helps Google deliver search results faster? Boom. Oh, I didn't start iClicker yet. Let me start iClicker. There we go. All right, I'll give you like a minute. Probably shouldn't need that much, but that was strange. Give it a minute. I don't know what the student side of things looks like, so. All good? Yeah. All right, I'll give a few seconds and then wind this thing down. All right, ding, 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 that's time, okay. So, correct answer, see what people put. Ah, good. Correct answer is in fact D. If you clicked on E, I hope you just, hit the wrong button by mistake. So, the reason why it's all three, parallel processing, that's the idea. You have a big problem, you break it into a set of small problems, you assign each small problem to a separate piece of hardware. So they can all happen at the same time. So instead of having one server do one single big task all by itself that takes really long time, you have a whole bunch of servers, doing a little task that gets finished in a split second. Okay. Indexing, of course, that helps deliver stuff faster. Instead of searching every page in the database to find whether it's a good match with search terms, Google can instantly say, oh, this term is only found on these pages. It's a much faster lookup. Okay. And of course, caching, right? If there are a set of search results that are very popular, for example, I don't know. I imagine after the Dodgers won the World Series, there were a lot of cached pages around that, right? And of course, we had the election the other day. I imagine there's a lot of cached pages around that. So Google doesn't have to do the same search process over and over. So all those help the search results come in faster. All right. Okay. Cool. Well, interesting point about the internet. It was not designed by a single company or single government organization. It actually happened, in an organic way as well, we'll talk about it. I'm going to draw a really shitty map of the US. And then, all right, so there's Florida, I don't know, something, Baja, whatever. Okay. So that is pretty terrible. Okay. Anyway, that's fine. So internet started over on the West Coast, right? 1969, there were 4 research operations that said, gosh, wouldn't it be nice if instead of printing out punch cards and hand delivering them to each other, wouldn't it be nice if we could just hook up some cables between our operations and transmit the data electronically? And everybody agreed that, yeah, that'd be a lot better. Why don't we do that? Okay. Well, needless to say, in 1969, there's no instruction booklet on how to do this, right? Nobody's ever done this before. So you have some basic issues with what are called protocols. Okay, so protocol just means standard way of doing something, right? So I guess it's kind of funny that this late in the time of the universe, we all probably have a fairly standard frame of reference around Star Wars, right? You guys all know who C3PO is, right? Yeah, C3. Okay. So one of C3PO's first lines is when he meets the humans, he's like, "Oh, I'm a protocol droid, right? I'm for etiquette and protocol." You may recall that line. Protocol is just a standard way of doing things. Okay. So for networks, you need a standard way to locate a machine in a different network, right? So if you're just talking about one machine in your own network, all you have to do is hook up a cable to either end of it, right? Cable to one machine, cable to the other. Boom, they're connected. They can transmit data, right? But if you actually have to find that machine in another network, well, suddenly you don't have that capability. You have to develop basically an electronic postal system. So you have to have a way to find that other network. You have to have a way to locate a particular machine in that network. You need some kind of addressing scheme like IP addresses, okay? So you need a standard way to locate a machine in a network, standard way to find another network, right? And a standard way to deliver data, okay? So all these kind of things, you need standard ways to do them, and we lump those together under, what are called protocols. Okay. So first one over there, and let's say, for purposes of discussion, say that shortly afterward, there's another one in the vicinity of New York and Washington, D.C., where there's 4 similar networks, and they say, hey, same kind of thing, right? Wouldn't it be nice if we were all connected? And they say, yeah, it's a great idea. Let's do that. So you have this point in time, you have 2 networks, right, that look kind of like Purina dog chow things. And the question is, if you're going to join those 2 networks, how is that going to work out? Okay, so for this next part of our presentation, I need 2 volunteers to play a game. It's not highly competitive. Just need people that aren't afraid to talk out loud. Okay. We got 1. Thank you, sir. Very brave. We got 2. All right. Excellent. Okay. Well, you rose your hand first, so you get to be red and you get to be green. All right. Now, the game we're going to play is you have to make up some good sounding stuff about why, when these 2 networks merge together, you should keep the protocol you already have, right? Red obviously would prefer the network to keep Red's protocol, so they don't have to change anything. Green would like to keep Green's protocol, so they don't have to change anything. Okay, so Mr. Red, convince Green about why the network should speak red instead of green.
We established our network first, so we have a longer history. I want to say too, our framework is more solid. That's my pitch for the day.
All right, all right. What's your response to that? Excellent. Okay. This is actually pretty close to how shit went down in real life, right? They argued about performance. Red said, hey, our protocol is better because blah, blah, blah. And Green says, well, yeah, but our protocol is better because of blah, blah, blah. Okay. Maybe they pick one, maybe they pick the other, but they have some kind of mutual interest in having a well operating, a well run system. So at some point they'd agree to use some updated version of one or the other and call that purple. Okay. Now, what happens at the time, right? Other operations, other networks appear all around, and one by one, they join and start using purple. Okay. Without worrying too much about the details of why that's happening, we're going to say simply that that is what happened. Okay. So we have a whole bunch of networks all speaking purple. Okay. Now, at some point, another network pops up, little cluster up here. We'll say it's by the Twin Cities, which actually used to be a tech hub, like a significant one. Hard to imagine now, but anyway, so now we have this smaller network called blue, and we're going to repeat this exercise again. So you get to be purple and you get to be blue. And now purple, it is your chance to convince blue why when your networks join together, why that should speak purple instead of blue, and vice versa for you.
I'd say we already are clearly established that we can support this bandwidth, like we can do the job, we can get it done, there's no question about it. I don't necessarily know if, this new method of, executing tasks is necessarily going to be able to, hold exactly the amount that we have.
All right.
We are well established.
All right, that's fair. What do you got? What's your counter, Blue? All right, cool. Well, believe it or not, that too is most of what happened in real life. What happened is simply the bigger one, the practical reality of it, since purple is so much bigger at this point, it's going to be very expensive for purple to switch over, right? Purple doesn't want to do that. It's going to not only switch how people are doing things, make new documentation for everybody, it's going to be a big hassle, right? Whereas if blue switches over to purple, the costs are relatively small. Also, consider the fact of, how much blue needs purple versus how much purple needs blue, right? Purple's already a pretty big network. It would be nice to have blue added on, but realistically, it's they're not going to adopt blue's protocol overnight, right? Whereas basically what's going to happen is purple says, well, if you want to join us, you got to speak purple. If not, good luck. Now, what can happen though, there's a footnote to that. If it turns out that there are in fact superior techniques involved in Blue's protocol at this point, that sort of stuff could get implemented in a new revision of the protocol, right? So they're not going to do it overnight, but they might say, gosh, Blue, you got some really good features there. And when we update our protocol next time around, yeah, we're going to include some of them. Okay, so they can still learn from each other, even if those updates aren't going to be implemented right away. Okay, and that, again, that's pretty much what happened. So the networks join, they all speak purple. And the important takeaway from this, right, it's not like the government stepped in and said, you're all going to speak purple. It just makes sense to pick one way of doing things. Just like, for cars driving on the road, it doesn't matter that much whether a country picks that people drive on the right or they drive on the left. What matters is that within a country, everybody agrees to do one or the other. All right. Cool. So anyway, that's how it happened. Okay. Now, this stuff. Talk about the structure of it all. Blow this up so it's easier to see. Okay. So I'm going to start labeling some things in here. The backbone here in the middle is high speed, high capacity fiber optic cable connecting distant parts of the world. Okay, so anybody ever play Minecraft with a LAN setup, local area network, where it's like just people on one side of a router? I see a few heads nodding. For the rest of you, I hope you know what I'm talking about. Okay, so I'm going to box this for a local network. So a local network, local area network, all the machines under a particular router, right? Usually in one building, like a house or an office or a computer lab. Okay, something like that. That's what we mean by a local area network. Okay, now what happens if you want to send a message to somebody else in the same local area network like that? You send a message, it goes up to the router has a list of all the connected users, and it could say, oh, yeah, you want to send a message to Joe? I see Joe is in one of my users, he's on my list, so I just send the message to Joe. The router can handle that, okay? But if you want to send a message to somebody in the next building over, you need some outside process, like in this case, a regional network, okay? The regional network, I'll say here, governs groups of local networks, okay? So if you have a regional network, what'll happen is you want to send a message not to Joe under your own roof. You want to send a message, I don't know, to your boss, who's in a different city. So your message goes up to your router. Router looks at it, says, oh, your boss, his IP address is not on the list of connected devices. So the router says it's not in here, so I'm going to kick it up towards the backbone. Regional network. Regional network looks at that list of IP addresses, says, oh, yeah, he's here. I know where to send it. He's in this local area network. So it doesn't have to go to the backbone. Okay. It can be handled just through the regional network. However, suppose you have a friend on the other side of the world, right? And your friend this is George in Sydney, Australia. Okay. And George is over there and you want to send a message to him. Well, what's going to happen to that is you send the message to your router. Router says, oh, George isn't on my list of users, so kick it up to the regional network. Regional network looks at it and says, hey, that's an Australian IP address, because you can look at the IP addresses kind of like the international codes or area codes on phones, and you can see where that user is. So the regional network says, oh, he's not over in my region. I got to send that message up to the backbone. So send that message to the backbone. The backbone knows which regional network to send it to, because like I said, the message basically has an area code on it. So sends it to the Australian regional network, which says, okay, I know which local network George is in, sends it to that one. The router sends it to George. Okay, same kind of process, but that's how this whole backbone reaches everybody. Okay, local messages may not need to touch the backbone at all, but if you're sending something to the other side of the world, it does. Okay, now it is worth mentioning this particular drawing is set up like a tree. And when I say set up like a tree, it's set up so that for any particular user, right, for any particular pair of communication endpoints, there's going to be exactly one path to get to them, right? But in reality, for reliability, the internet isn't set up like that at all. So I say here, although shown as a tree, internet is a web of interconnected networks with many routing paths between 2 points. Even if some infrastructure fails, data could flow. Okay, so I'll give an example of that. Okay. Suppose you have two components, A and B. They could be routers, they could be switches, doesn't matter. They're some kind of communication devices, right? If you have one single line connecting the two, and there's a break in that line, like a rat chews through the wire or something, can A still communicate to B? No, because there's just one line, right? Okay, that's fine, that's fine. Okay. However, suppose there are two lines. Okay. Now, in this case, it is true that if one of the lines breaks, there's a backup line available, right? So the rat would have to chew through both. However, the problem with this simple setup is these particular links are set up through what are called ports, right? Similar to the ports you have on your own laptop or whatnot. Okay. Now, internet designed for reliability means that any combination of a single failure on every machine in the internet is not going to cause it to shut down. All right. So yes, it could survive one of these cables being broken. I wanted to do an X there, but what it can't survive, if this port on A breaks down and the opposite port on B breaks down, right? If those two ports become unavailable, then even though both cables are there, right, they can't communicate. So what happens is it's set up with extra redundancy built in. Okay, so there are extra connections. And by setting it up like this, even if this port breaks down on A and the same one breaks down on B, well, guess what? You can still send data over this line, right? So A and B can still communicate. There's no combination of a single failure on both A and B that's going to cause this setup to fail. And this sort of setup, again, in the tree diagram we had, everything was portrayed as having one single path. There are also going to be backup parallel paths like this next to each other. So if this particular combination of A and B breaks down, there's a backup combination of A and B, available. All right, so that's all what's called redundancy. And I know that you've probably, if you've heard the word redundancy before, it's probably been presented as a bad thing. Like you write an English paper and your teacher says back, this is redundant, right? Meaning you've already said it before, you don't need to say it again. But in this case, redundancy, it's a good thing. It means reliability. The downside is, of course, it costs more money, right? More hardware, more cash. But if your bigger goal is to keep the internet running, you're going to need that kind of redundancy. So one rat chewing through one wire doesn't ruin the whole thing. Okay. All right, we'll do a question, then we'll come back and we'll talk about ISPs. So another question, it's question time. Do 27. Dun, dun, dun. Okay. By the way, I did get caught up with, I had a few students asking me about some irregularities in the lecture questions, and I just hadn't been updating them for a while. So, like I said, the iClicker software, the platform, by default, it sets it up so you get a point for showing up. And there's another thing where you get a point for asking questions correctly and another point for answering like 75% of the questions. Those are the default settings. I can't change those. So for every session, I have to go in and manually update them to just give credit for questions answered and nothing else. And so I hadn't been doing that for a few weeks. And anyway, so in case anybody had any concerns, up until today, we're all caught up to date. Yesterday, I went in and I updated all of that through yesterday's sessions or Tuesday's sessions. Okay. 10 seconds, I guess. All right. Ding, 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 ding. Okay. That's that. Okay. What's the right answer? Let's see what the survey says. Yeah, good. Okay. Pay-per-click, right? Pay-per-click is the main revenue model. Other ones are out there, but pay-per-click is the big one. Okay. So ISPs. All right. So ordinary users like you and me, we don't connect directly to the backbone, right? We see, like in this drawing, we connect through some internet service provider to get there. And the closest analogy to this for me is water pipes. Okay. So the backbone is like the massive, 24-inch or bigger pipes for the water mains, right? If you don't know what a water main is, basically really big water pipe. Okay. Every now and then, water mains over by Lakeshore Drive bust open and they flood so I see people know. Okay. Now, anybody happen to know what the typical household water connection pipe size is? Anybody want to take a wild ass guess? Not even. It's like an inch. An inch is pretty standard. Okay. Anyway, that's okay. I wouldn't necessarily expect people to know that, but if you've ever like hooked up a garden hose to the side of the house, it's about that size. Okay. Nothing like a 24-inch pipe. Now, everybody needs water in their house, right? And wouldn't it be nice if everybody had a 24-inch pipe so they could get all the water they need pretty instantly? Well, kind of, right? But giving everybody that capacity to get water creates some problems, right? One of the big problems is simply what happens if everybody in the neighborhood turns on, that opens up that big 24-inch pipe all at the same time, right? You're going to need a far bigger water main pipe to supply that, right? Or you're going to have to build really gigantic water towers or have like one gigantic water tower per block because it could get emptied really fast. Okay. So same kind of thing with this. The backbone, fiber optic cable with incredibly high capacity, right? You don't connect directly to the backbone on that kind of connection because if everybody has a connection like that, the backbone has to have orders of magnitude more capacity than it already does, right? And you could say that, yeah, me as a single user, sure, wouldn't it be nice to tap in straight to the backbone? Yeah, sure, but it creates system problems, right? other stuff, the hardware is going to be more expensive, just like it's more expensive to have a 24-inch pipe, going up to your house. If it breaks, it's going to be a huge hassle to fix, right? As opposed to a 1-inch pipe that breaks, you walk over to Walmart and buy a new, slice of 1-inch pipe, whatever. Okay, so same kind of problem. This is why ordinary houses don't connect straight to the backbone. The regional network not only, handles sending the data through, but it also effectively provides some kind of regulation of what individual users are doing, right? Because each individual user has a relatively small water pipe for data. And so the regional network can manage, all those connections going to the backbone so they don't get overloaded. Okay. Now, all of these internet service providers, there are 3 different tiers of them. So tiers, once again, just means groups of things doing the same kind of thing. So tier 1, those are the big ISPs, the ones you've heard of like AT&T, Verizon, Sprint. What makes them tier 1 is that they own a big chunk of the backbone. Okay. And we'll talk about why in a moment, but because they own a big chunk of the backbone, they can connect to any other network using what are called peering agreements. Peering means they don't pay to send data, right? They send data for free. Okay, it's basically because they own a big chunk of the infrastructure themselves, right? So tier 3, on the other hand, those are what are called last mile providers, right? Those are the guys that have the little water pipes going straight up to your house. So last mile providers, they only use paid transit to send data. So that means if they want to send data to another ISP, they have to pay to do it. Okay, and tier 2 are the ones in the middle. They connect tier 1 and tier 3 networks. Okay, and they might have a mix of those. So a tier 2, if it's sending data to a tier 3, does that for free. If it's sending data to a tier 1, it's got to pay. All right, so I'll show how that works in practice. Okay, so talk about, again, me in the corner here, and I'm sending an email to my buddy George in Australia. I'm trying to anyway. Okay, so when I send the data to my router, is that going to cost anything? You think it's going to cost me anything to send a message to my own router? No, that'd be crazy, right? Yeah, that's free. Okay. But when that router sends data up to the regional network, right, I got to pay the ISP for that. Okay. I have to have a membership in an account with the ISP, so I have to pay Comcast. Okay. If Comcast wants to send that to the backbone, right, and we're assuming for purposes of discussion that Comcast is not in fact tier 1, when in fact they largely are. But if you want to say a regional network wants to send something up to a backbone, it's got to pay for that, right? But once the backbone gets it, it no longer has to pay. I should have not grabbed that color so soon. Okay, there we go. Okay, so sending stuff on the backbone, that's now free. I'm drawing it in blue because it's free. And when it gets sent to that Australian regional network, that's going to be free, not going to pay for that. Okay, and when that Australian network sends it to George, likewise, the ISPs aren't going to take any money. So sending data toward the backbone, they have to pay. The ISPs, they get subscription fees for people. They use it to pay all of these, backbone owning tier 1 ISPs for the privilege of using the backbone, right? But the tier 1 ISPs themselves, they're basically an assumption of reciprocity, right? The data going one way is going to be balanced by data going out the other way, and it's not worth the hassle to track every little bit of data individually. So they just say, yeah, you can send it for free. Same thing for the backbone sending data to regional networks and local networks. Again, the assumption built in that it's already been paid for going one way, so there's no point in tracking it, going the other way over those same kind of networks. All right. Now, interestingly, about 25 years ago, these classifications were pretty strict, right? Companies said, I am going to be a tier 1 provider or a tier 2 or whatever. But now it's blurry, and Comcast is one of the big blurry ones. So Comcast started out as tier 3, right? Just doing connections straight to your house. And officially they're classified as tier 2 because they don't have enough backbone infrastructure that they own everywhere they operate. So because they're not a tier 1 everywhere, they're classified as tier 2. But in the United States, they're pretty much a tier one in like 99% of the places where they operate. The only places where they're not is there are some places where getting the infrastructure, getting that chunk of backbone would be prohibitively expensive, or otherwise operating there would be. So it's kind of like the Postal Service, right? One of the downsides of being the US Postal Service is that they have to deliver mail to the house of anybody, even if they're somewhere remote, like way out in Montana and they're like 10 miles from the nearest mail station. Postal Service still has to deliver mail to those guys, right? Whereas, somebody like UPS or FedEx, they might say, nah, we're not going to do, delivery straight to your house. Or we're definitely not going to do that the flat postal rate, right? We might deliver it to the station for a standard cost, but we're not sending a truck out there 20 miles for your one package and expect that you're going to pay 39 cents for that. Okay. So same kind of thing going on with Comcast. Comcast kind of picks and chooses certain markets to stay out of because it's too expensive to operate there. All right. Anyway, so the tier one, tier two, tier three thing, it's a useful classification for understanding what's going on, but recognize the real world isn't really like that anymore. Okay. And here's an image of the same stuff with some links if you are interested. Access ISPs here, same thing as tier three. Okay. Now, back to this peering versus transit bit, right? So I don't know if anybody's ever sent an international letter, but if you have, you might have wondered, hey, I'm sending this letter to France. How come I don't put French postage on it, right? How come I just get an American airmail stamp and that gets the letter the whole way there? Kind of crazy, right? Once that letter gets to Paris, the French postal system has to handle it. How come I don't put a French stamp on it? Well, again, same thing, assumption of reciprocity, right? There's an assumption that for every letter going from the US to France, there's going to be a letter coming back from France to the US. And in the end, right, both postal services will about break even. And if there's some gross mismatch in the volume of mail, well, they can say, oh, well, you took, 8 plane loads of mail this week, and you only sent back 2. So there's some mismatch, and we'll exchange some money and it'll all be fine, right? It's easier to just worry about the total sum of traffic instead of managing every particular letter, right? And that's the same idea with networks. So these big tier one networks with the backbone, they're sending tremendous amounts of data all the time, right? And any message you send is basically broken up into what might as well be mini files called packets. Packets are pretty small, about 1.5 kilobytes each, and they are dealing with, a lot of those packets. If they had to constantly track and tabulate and charge people for every individual packet, that would be a lot of work for very little practical purpose, right? So instead, they just say, you know what? We're sending data one way for free. You can send data through us the other way for free. It'll all work out, right? And that way they don't have to deal with that stuff. The problem, though, in some situations, especially with Comcast, like if you're interested in reading about that, it's an article from about 10 years ago, how Comcast exploited some of that. There are some cases where there are massive traffic flow imbalances, right? So Netflix was a big one, and Comcast took advantage of that. So the idea is if you're sending a request to Netflix to watch a movie, that request is going to be a pretty small data object, right? Basically, your account, the name of the movie, that's about it, right? But when Netflix is sending that movie back to you, that could be a couple gigabytes of data. That could be huge, right? And if those sort of imbalances, if you can position your ownership of the network so you're only paying to send, the little messages one way, and somebody else is paying to send the big download file, the big movie file the other way, you can get by with a lot less infrastructure. Okay, that means you have a lot lower operating costs, means more money. So a lot of these other ISPs, they kind of hated Comcast for that. So anyway, so that's the idea. So again, big ISPs, they use, tier one, they use peering agreements. They don't pay for what they send. If things get really out of hand, eventually there's going to be some legislative or litigation type fix to it. But, they'll have to work that out later. They're not going to work it out in the moment. Okay. So rest of what we're going to talk about today, just a few slides. We're going to finish a little early, which is fine, will be routing. So routing basically means sending data from one network to another. And sometimes it gets used for internal routing, like sending around data within a network. But most of the time when you hear people talk about routing, they do mean sending data from one network to another. So like this image I had a bit back here, if I can get to it. I don't know if I can. I should be able to. That one, all those little boxes, those are networks, right? And the issue we're talking about is how do I get data from one network to another? Okay, and just to mention, this was my field back in the day. This when I did my dissertation many years ago, it was around, I started off on that when Facebook's model for ranking was kind of new and interesting, right? So we talked about the edge rank model where posts are ranked about whether they're new and depending on who is using them and how many people, like them, stuff like that. We had a similar idea for, imagine if you're in some setup where there are a bunch of mobile devices running different applications and there's limited bandwidth. How do you decide which applications get to run where, right, without any sort of overarching supervisory infrastructure, right? If you have some governing process that says, you're Doug, you have elevated access, and you're Fred, and you don't have elevated access, that's managed, right? But if there's no kind of infrastructure like that in place, come up with a way to reasonably fairly allocate which applications get to do what, right? So because of that, I knew a bunch of stuff about routing protocols back at the time, most of which I've forgotten, right? So, but once upon a time, this was my stuff. I don't really do much with it anymore. Okay. So the internet has millions of host computers, right? Host computers, they mean they have data that people want. So we'll call them servers, which provide data and services as requested by clients, right? Ordinary people like you and me mostly. So for typical internet use, the way it works, your device will send a request to a host system, right? For example, you want to see a web page, your device will send a request to a web server, say, hey, show me such and such page. Web server digs through its database, pulls the page, maybe constructs it partially, and sends the results to you. The way it's going to send is in what are called packets. So packets, think of them, like I said, as mini files, right? So a typical image file might be 2, 5, 10 megabytes. Packets have a maximum size of 1.5 kilobytes. And we'll talk one of these days in the YouTube module about why packets are small and why it's a good idea. But packets, they're these small mini files. So if you have a big image you want to send over the internet, it might very easily get broken up into thousands of packets, each of which is sent sequentially over some path in the internet. Okay. So that path of all of those routers is called the routing path. All right. So that's what we're getting to. If you want to send data over the internet, it gets broken into pieces called packets. Those packets get sent over some sequence of devices called the routing path. Cool. All right. Now, I have this lovely image here, which I'm going to lift. Okay. So I'm going to do the key over here. Big blue dots are the routers. Okay. So there are many routers. The pink lines are the connections between routers. Right. So think cables. And finally, the red boxes are packets. Okay. Packets of data. Okay. Now, if you as a source want to send a message to some destination device, and it doesn't matter if it's you sending a request to a server or the server sending a response to you, in either case, you have to figure out how to send the data. Okay. So there's going to be a lot of different pathways. In this particular map, you could see, I could start off doing something like this, or I could do this, or I could do that, or any number of other similar combinations, right? Fairly direct paths to get to where I'm going. Okay, so routing protocols consider, number one, how to build a new routing path, right? Imagine if there are two devices on the network that have never communicated between each other before. How do they find each other? How do they send a message to each other? So they have to build a routing path. Number two, managing existing routing paths, right? Things like timeout and, refresh, right? Anytime there's a routing path, you might want to see, hey, should this thing timed out? We haven't used it very often, right? Maybe the source sent a message at 8 a.m. and then hasn't used that same path for 12 hours until it wants to communicate with that same destination again. Well, it's entirely possible that the state of the network has changed and what used to be a perfectly usable good path is no longer viable, right? So the question is, how often do you do that timeout? And how often do you do checks? Do you do checks at all, right? So those are questions. And of course, when do routes expire? Okay. And how to respond to failures. If you try to send a message and it turns out that, oh, this routing path is no longer available. Well, what do? Well, the routing path has to do something with that. Does it create an entirely new path and try to send the entire message? Does it think that a certain number of the packets got through and it starts again with the ones that didn't, right? Or what? Something else entirely, right? And how long does it take to determine that a path has actually failed, and how does it determine that? So routing paths, routing protocols are concerned with all those sorts of things. Now, there are two main families of them, two main approaches to routing. One is just looking at what's called a hop count, right? So two main approaches, well, let's call this two main classes of routing protocols, okay? One is simple and just uses hop counts, right? So in that case, what we're talking about is the number of routers between the source and the destination, right? So here you might say, okay, this is a pretty direct path. I'm trying to draw circles here. So I might do 1, 2, 3, 4. That looks pretty direct. You're not going to find a faster one, right? Or a lower hop count, but there's a lot of 4s. So the question is, how do you figure out, which 4 you're going to use? The advantage of the simple ones is, of course, they are simple. They are easy to build, easy to construct, okay? Which I guess is the same thing. Easy to manage was what I was looking for. But the downside is they may not perform that well, right? So, for example, you may have decided that this particular path, which has a hop of 4, is really good, right? But it could be there's a lot of cross traffic coming this way that interferes with it and makes this particular stretch of the internet very, very slow, right? Because you have a lot of traffic from your source to the destination and a lot from that way. And a simple routing protocol isn't going to check for that. It's just going to look at the hop count, okay? So in some cases, if that sort of problem is not likely to arise, this simple model is probably perfectly fine, and it has the advantages of being quick and easy to maintain. On the other hand, the other one is where, bless you, where you track performance, okay? So I'll say here, complex, and uses what is called link state. So link state is the state of the different links between the routers, right? The state of these pink lines. So one typical way to do that with response times, or what's called latency, I guess. So you might say, hey, getting a message across this link, that takes 10 milliseconds. Getting a message across this link takes 6 milliseconds. Because of lots of traffic, getting a message across that link takes 30 milliseconds, right? And you have that kind of data for every link in the network. And so basically, when that source wants to send a message to the destination, it can look at that map of link times and figure out what the fastest path to get there is. And it picks that path. The downside of the complex one is, of course, number one, it's more work to gather all that data. Number two, especially for a bigger network, right? A small network like this, not a big deal, but a big network might have many, many links, and it has to be shared with every device in the network. Number two, those links, the state can change pretty quickly, right? From being slow to fast, depending on what's going on. So there has to be very regular refresh going on. Otherwise, what could happen is it would be like you get in your car and you pick a route to UIC because the travel app says, oh, this route is not at all congested, right? And then halfway through, you find that they just started doing road construction on the way in. And it's like, oh, now it's going to take me an extra half hour to get there, right? That's the sort of thing that can happen if you don't refresh those times frequently. But again, the more often you refresh them, that's going to clog up that whole network with basically that overhead of route maintenance data. So the complex ones, when they work well, they can work very well, but it's also possible that they don't work well. And it's going to be, in any event, there's going to be more management effort required. So just to get that out, there's a couple different models. So simple routing protocols might use path length. Others include factors like traffic load, connection speed, basic different metrics for link state. Okay. Now, most internet traffic uses HTTP, Hypertext Transfer Protocol, which sends all of the basic way that works, sends all the data over a particular path. So TCP/IP, if you've ever heard of that, Transport Control Protocol, that is going to send all the data over a particular path. So the source will pick one route to send the data over, and then every packet in that message will use that same route. That's the standard model for the internet. There are alternatives used on the internet, but that kind of TCP traffic is about 95% of what's going on out there. Anyway, we'll talk more about that in the YouTube module. This is all the new content I wanted to bring. We'll come back because this is a good break point. But any questions on any of this? I mean, yeah.
Was because, like in your example, for instance, so it's the local networks, then it's regional, and then it's the backbone. So
Yep.
on the example, it's like only a couple of local networks connecting to the example. Like, just to understand how big are they going to be, like a typical regional service.
Well, when we talk about a regional network, we mean something like, northeastern United States, right? So we could look that up, right? How big are regional ISPs? Okay. Significant players in their local areas, right? So they say over 2,700. I mean, there's probably a handful of big ones. I don't know exactly, the count you'd like to throw in for that, but let's say a couple thousand in the US. And so you can do some math on that and figure that each one probably governs a few 100,000 on average. Yeah. Okay, cool. Good question. All right, well, then I have a question for you. Let's do this thing. All right, what do we want to pick? Oh, I went up today, didn't I? 16. All right, we'll see if you guys did better than the morning class. Morning class had trouble with this one. All right, I guess that's it. I'll give till 120. I know you're all waiting to see what the answer is. It's gripping. So much drama. All right. Ding, ding, ding. Okay. Correct answer is, oh man, you guys had trouble too. Who put down E? There you go. All right, round of applause. E is the correct answer. Okay. So reason why you have column families, a column family deals with the problem. If you want to have a relational database, every field, every record has to have the same set of fields, right? But a web page could have dozens, even hundreds of images. So to put web page data in that kind of structure, you need dozens or hundreds of fields. Well, that's crazy. You don't want to do that. That's going to create a lot of empty, wasted space in the database, right? Because most pages don't have anything like that many. So instead of putting all the images in separate columns, you basically have one column that links to a list of images somewhere else. So that lets you have a single column in a relational database reference non-atomic data, right? Data that has multiple things in it. That's why you have column families. All right. All right, cool. We'll see you all next time. It's been a hoot. What's happening?
The question to average performance.
Oh, that's weird. You were here for 1 and 3?
Yeah, one in
Okay.
three is perfect.
All right. Send me an email. What's your name?
Christopher Pena.
Okay. Send me an email. It's fine.
Yeah, just love it, literally.
I'll give you the benefit of the doubt. Yep, no worries. Yep,
I'll send it to you right now.
cool. Thank you. What's happening?
I was wondering if you teach any of these IDS courses,
I
but
can't read too far.
because I know when I go on the portal,
Oh.
sometimes the teacher doesn't pop up.
Yeah, once in a blue moon, I teach 401. That's usually over a summer session though, although you never know. There's been a lot of shakeup lately.
Okay,
The only other thing I do teach 313, but that's only in the fall.
and then out of those, do you know like which ones like should be taken or?
I mean-
It's like open to which one do you want.
Yeah, do you want to learn to code?
I was originally like a CS major, and I did some coding, I didn't really, but it's not terrible, but I've never done.
Yeah, but I mean, my question is, if you want to code,
Mhm.
all right, there you go, sorry. Yeah, welcome. If you want to code, I would take for sure 401, right? And 400, once you've taken 201, do you have like C++ experience or something? I don't,
Yeah,
201,
Yeah,
okay.
I took 201,
Okay.
I did see like an advanced C++ course, because I
Okay.
transferred. my
Did you
course
take
from-
201 from me?
No, I went to a community college and I took C++ there. and
Yeah.
I transferred, and then
Yeah.
they took it as 201.
Gotcha. Yeah, if you can do C++, you can do Java, so
Okay,
now, but 401 is advanced Java,
Okay.
and so. Yeah, I mean, have you coded in Java before?
no,
Yeah, so there are some differences, right? I mean, a lot of the syntax is really similar, but the big difference with Java is that you don't reference